In this video, we're going to take a look at section 7.2 on estimating a population mean. So in the previous video in section 7.1, we were estimating population proportions using confidence intervals. We're going to do the same thing in 7.2, estimating population means using confidence intervals. And while the structure is essentially the same, the details are all different. So, as we talked about in the previous video, a point estimate is a single value or point used to approximate a population parameter. The sample mean is the best point estimate of the population mean. So if we had to pick just one number to estimate the population mean, the best number we could pick is a mean from a sample that we have collected, presumably randomly, right? That's the gold standard for that. So on the homework, if they ask you to find the best point estimate of a population mean at any point, you use the sample mean as the best point estimate. And you just type that number in and that would be the answer. All right. However, what we want to be able to do in this section is to provide a ranged estimate. So we want to give a set of numbers that the population mean might be between. It could be as low as this number or as high as this number. So we want to give a range of values to estimate the population mean. The confidence interval will allow us to do that while also having a confidence associated with that estimate, right? That we actually build into the calculation. And so we will not only be able to give this estimate that the population mean might be between this and this, but we will also be able to quantify how confident we are in that estimate. So, here's where things get a little bit confusing. And I don't really like the first one, but it's part of the material, and maybe I'm wrong about my intuition on this. But if the population standard deviation is known, we have one path to take. And if the population standard deviation is unknown, we have another path. So notice these two bullet points, the first phrase in both of them make that distinction. So in the first case, if the population standard deviation is known, then the distribution of all possible sample means, is a normal distribution, which we represent with the letter Z. And so it'll just be a normal distribution. You'll do Z-scores, you'll do, inverse norm, normal CDF, whenever you're doing calculations involving finding the confidence interval for a mean if you know the population standard deviation. But that's where I have an objection, because we are trying to estimate the population mean, meaning we don't know it. We're trying to find an estimate for it. But yet we somehow know the population standard deviation. I don't know. That doesn't seem right to me. Like, if we don't know the mean, how do we know the standard deviation in that case, right? But we will do some problems, or some in the homework, that we are going to assume that we somehow know the population standard deviation, even though we don't know the population mean, and we're trying to estimate that. And in those cases, we will use the normal distribution to calculate the margin of error, the critical value, all that stuff. We'll use the normal distribution. Again, I find that it's unrealistic. That's my opinion. Maybe I'm wrong about that, because again, my statistics is not my background necessarily. And so if I'm wrong, please, if somebody's watching the video, comment on my video and let me know. I think the more realistic scenario is that you don't know the population standard deviation either. Now, you might have estimates for it. So the example we're going to see later, it's going to say studies have shown that this is the estimate for the population standard deviation. But again, that's just an estimate. You don't know that's the population standard deviation. So let's see. Okay, what's going on? I think I froze up here. Sorry. Okay. Now, so the more realistic scenario, in my opinion, would be not knowing the population standard deviation. In that case, we have to use the sample standard deviation as an estimate for the population standard deviation, right? So if the population standard deviation is unknown, then we have to use the sample standard deviation as a stand-in for the population standard deviation. This introduces another level of uncertainty. So the normal distribution is no longer the best description of the distribution of the sample means. Instead, we will use the student t distribution. So we'll be using a slightly different distribution to describe the sample means in order to develop our confidence interval. And it's called, for short, the t distribution, but the official name is the student t distribution. All right. So here's the difference in the formulas for calculating a t value versus calculating a z value. So z for the normal distribution, t for the student t distribution. And notice, and we're not going to be using these formulas. I just wanted to show you this comparison. We're not going to be using them yet. We will be using them in Chapter 8 for calculating test statistics. Right, that's something we'll talk about in that section. But notice that these are essentially identical, but the difference here is here we use a sample standard deviation, whereas here we're using the population standard deviation. So if we know what that number is, we use the normal distribution. It becomes a z-score. If we don't know what this number is, we use the sample standard deviation instead, and it becomes the t distribution when we do that. All right. So here's an example of what the t distribution looks like in comparison to the normal distribution. So I don't know, I'm having a little bit of trouble seeing it from my angle. So the blue one is the normal distribution, the standard normal distribution. That's the bell-shaped. They're all bell-shaped curves here, really, but the normal distribution is the blue one. The pink and orange one are t distribution. So you'll notice that they're fairly similar looking, but they're not quite the same as the normal distribution. And notice the shapes are different there depending on the sample size. So the pink graph is a t distribution with the sample size equal to 12. The orange or yellow graph is the t distribution where the sample size is equal to 3. Now, the bigger the sample size becomes, the better the t distribution matches the normal distribution. So you can kind of see that starting to happen as you go from 3 to 12. If you went from 12 to 30, it'd be even closer to matching the normal distribution. All right, but the values will be slightly different. So when I go to calculate a critical value from a normal distribution, and then I compare that to the same critical value for a t distribution, same confidence level and all that stuff, you'll notice that the values are going to be slightly different. But they'll get closer and closer as the sample size increases. I think that's right. I don't know. I'm kind of nervous. Like, is that true? I think that would be true. I think that'd be the case. I don't know. I guess we'll find out. We'll do some examples. We'll see. Maybe as we're calculating these critical values for t, we can always compare them to what we would have gotten if we were using the normal distribution, just to see how close they are. All right. Now, in calculating the t values, the critical values for t, as I mentioned, it's the sample size affects it, but we don't address the sample size directly in calculating the critical values for t. When we calculate a t value, we instead describe it using degrees of freedom. So the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. So it's a pretty abstract concept that gets glossed over in the textbook, and I'm going to probably do about the same thing, kind of gloss over it a little bit. It's a simple thing to calculate, but the idea is fairly complicated. The best way I can think to describe it is imagine that the answer is already determined. You already know what the answer has to be for a given calculation. How many numbers can you allow to be anything you want before the numbers have to start being well defined in order to get the answer that you're supposed to get? So for example, consider that we're going to add 3 numbers together, right? So we're going to add these 3 numbers, but we already know the answer. The answer has to be 10, right? Well, in this situation, I'm adding 3 numbers, but 2 of them could be anything. There's no restrictions on these 2, but the third one has to be chosen just so that way when we add the 3 numbers together, it will add up to 10. So the third number there's no freedom. It has to be chosen exactly to produce the answer of 10. Right? So for example, I could pick the first number to be 5. I could pick the second number to be 2. I just made those numbers up. They could have been anything I wanted them to be. That was my freedom, right? I could choose anything I want for these two numbers, but I don't have a choice for this third one. If I know the answer has to be 10, then this third number here has to be 3. I didn't have a choice there. It was determined based on the answer we knew we had to get. So this situation, we would say, has 2 degrees of freedom. We're adding 3 numbers together, but there's only 2 degrees of freedom if you know the answer has to be 10. So it's the same for the t-distribution, that the degree of freedom associated with the sample that we have is 1 less than the sample size. Right? So the degree of freedom is abbreviated df, and it's just n minus 1. Whatever the sample size is, 1 less than that is the degree of freedom associated with that circumstance, that situation. And that's actually what we use in our calculations in our calculator. So when I go to calculate the critical value for t in these formulas that we're about to look at, I will have to let the calculator know what the degree of freedom is, which is not the same thing as the sample size, right? It's 1 off. So whatever the sample size is, I take 1 less than that, and that's what I type in as my degree of freedom into my calculator. All right. Okay, so requirements for constructing a confidence interval for a population mean. So here's what needs to be true in order for us to be able to construct a confidence interval in this situation. The sample is a simple random sample. That's almost always the requirement. The population has a normal distribution, or the sample size needs to be bigger than 30, and the selection of each element of the sample must be done independently. So as long as all those things are satisfied, you can construct a meaningful confidence interval that will give you a good estimate for the population mean. Okay, so here's the formula for constructing a confidence interval for a population mean. It's really similar in structure to the formula for a confidence interval for a population proportion that we saw in section 7.1. So we take the best point estimate, which is the sample mean, right? That's what X bar is. We've seen that since chapter 3, right? This is the sample mean, minus the margin of error. Right. Now, which we saw in the previous section, right? We had a margin of error in 7.1 as well. But calculating that margin of error will be different. The formula is going to look different. So again, same structure, it's margin of error. The formula is pretty similar. I mean, there's some similarities there, but the details are going to be different. The thing we're estimating goes in the middle, and in this case, we're estimating a population mean, so it's mu. We don't know what that's equal to. That's the thing we're trying to get estimates for. By taking the sample mean minus the margin of error, we get our lower estimate for the confidence interval. The lower end, I don't know what you'd call that, the lower bound of our estimate. And by taking the sample mean plus the margin of error, we get the upper bound of our estimate. So I'm just calling it the upper estimate here. Okay, so that's the top layer, right? But remember, just like in the previous section, I talked about inception, right? We have to dig down a layer because while we probably will know the sample mean pretty quickly, and we can just plug that into this formula, the margin of error takes a little bit of work to find. And so we have to take a moment away from this formula to go find that margin of error. So that's the next layer down that we have to go. Here's the formula for the margin of error. When we do not, now this is assuming we do not know the population standard deviation, and we're using the t-distribution because of that. And we're using s instead of sigma, because if we knew that, if we knew the population standard deviation, we would be using sigma here, and this would be a z-score in that case. But assuming we don't know the population standard deviation, then this would be the formula. S is the sample standard deviation. Sample standard deviation. Kind of got lost as I was writing that for a second. I was like, wait a minute, what am I trying to write? And n is the sample size. And again, S will either be given to you or you can find it on your calculator doing 1VAR_stats like we learned back in chapter 3, right? So 1VAR_stats can find us our sample mean and our sample standard deviation. So some problems, they just give you that information. They'll say the sample mean is this, the sample standard deviation is that. Other problems, they give you the sample, and they'll say, here's the sample data. There's 40 different numbers here. And then from that, you have to find the mean and the standard deviation for your sample. And the best way to do that is just type it into your calculator, do 1var stats. T is a critical value. So again, it's similar to what we were seeing in 7.1, except instead of a z-score, it's a t-score. And it's based on this value of alpha, which is the same thing as it was in 7.1. It's 1 minus the confidence level, right? So t sub alpha divided by 2 is called the critical value. Let's try that again. Sorry, kind of got written a little funny. All right. And finding that critical value is based on, the value of that number. I was going to say the value of that critical value. I don't know what I'm trying to say now. What's the best way to say this? What t equals depends upon the value of alpha. There's just too many values being referenced there. I was using that word too often. All right. So hopefully that just made sense. So what this will equal depends upon the value of alpha. So to calculate the critical value, I would recommend drawing a picture like we did in 7.1. I'm drawing a t-distribution, but again, the t-distribution is also a bell-shaped curve. It's just a little bit different than a normal distribution. And so when you draw a picture of it, it's not going to look any different, right? So this value is the t-score associated with the area in the left tail and in the right tail being alpha divided by 2. Just like it was in section 7.1. So we take our value of alpha, divide it in half, and put half of it in the left tail, half of it in the right tail. The easiest one to find is the left tail one, but remember, just like in 7.1, I'm just not happy with that. I recorded one video earlier for college algebra, and I was just really hard on myself with how I kept erasing and rewriting over and over. I haven't got that bad yet, but I'm afraid I'm starting to get there. I don't know why today it's bothering me so much that all these little ways that I'm writing that aren't exactly the way my handwriting usually looks, and they're starting to bother me a little bit more than usual. Which I said earlier, I'm like, I probably just need to take a break because I've recorded so many videos of all my lectures in the last month or two. And so I think I probably just need to take a break from that activity for a while. I'm almost done. So I just need to get done with it, and then I'll have a long break. So anyways, so I need to know what that t value is associated with this area being in the left tail and in the right tail. Again, technically it's this one here, the positive one. So remember that these will both be the same number, but one will be negative, one will be positive. But the negative one's the easier one to find because, again, at least in my calculator, when I use the function in the calculator, it wants to know the area to the left. And to find that critical value, I guess we didn't talk about this yet, it's inverse t, right? So inverse norm helps you find a z-score associated with an area to the left. Inverse t helps you find a t-score associated with some area to the left. So we're going to take inverse t of alpha divided by 2, and then that's going to come out negative. We'll get negative something, right? This is some number here. We just drop the negative sign and keep the number, and that's going to be the critical value. I'm sorry, I'm actually completely wrong on this. Sorry, making a lot of mistakes today for some reason. Not completely wrong. That was an exaggeration. Alpha divided by 2. Sorry, I forgot you have to have a degree of freedom in there as well, which I mentioned earlier, and then I just completely blanked on it as I was writing this out. So you need the area to the left for inverse t, comma, the degree of freedom, which, as we already mentioned, is just one less than the sample size. You have to let the calculator know what that degree of freedom is, or the function just doesn't run. If you forget to put that number, it'll just say error. It'll say, we can't find this for you because that's a necessary piece of information to do the calculation. All right. And you'll notice when you run that function, at least on my calculator, it hangs for a second. So it's obviously a fairly intensive calculation. Takes a second for it to do the computation and spit the answer out. But that's how you'll find the critical value. Now, alpha, we talked about last time, and it's no different this time. It's 1 minus the confidence level. And that the confidence level will be given to you in the problem. It's not anything you have to calculate or figure out. Okay, so that's how we put a confidence interval together, right? We'll be given a confidence level. We'll take 1 minus that to find alpha. Once we know alpha, we divide it in 2 to put half of the alpha in the left tail, half in the right tail. We do inverse t on that area that's in the left tail with a degree of freedom, and that gives us our critical value. We just drop the negative sign, whatever that number is, that's our critical value. Once we have the critical value, we can plug that in to the margin of error formula along with the stuff from our sample to calculate the margin of error. And once we have the margin of error, we can construct the confidence interval. Sample mean minus the margin of error, sample mean plus the margin of error. So that's the game plan. There's also a way to have the calculator do all that work for you. And I'm going to make, I still haven't done it yet, but if I have time later today, I will make a video on how to use your calculator to construct confidence intervals. So you can see how the TI-84 can actually kind of do a lot of that work for you. But in the video, I'm going to go through the process step by step. So even if you decide, I'm just going to let my calculator do all that work for me, at least you know what the calculator is doing. That's really helpful, right? If you have no idea when you run the calculator function and it tells you the confidence interval, if you don't really know what's going on with the calculator, how it's doing that computation, it's hard to really recognize if the answer is a sensible answer, right? You just maybe, without knowing what it's doing, you just kind of accept what the calculator tells you as the right answer. And so by knowing something about it, you might be better able to realize, oh, wait a minute, that answer doesn't quite look right. Maybe I typed something in wrong. You know, that's one use of kind of understanding what's going on, but also for interpretation, right? Understanding what those numbers actually mean, how they were arrived at. You know, if you just have this confidence interval and it's just these two numbers, you might have no conception of what those two numbers are telling you, right? So extracting meaning, drawing a conclusion from the confidence interval that you're provided by your calculator, you're better able to do that if you understand how that calculation was done. So I'm going to spend time on the video going through the calculation so you can see how these are put together, even if you're going to ultimately end up letting your calculator do that for you. Subjects were, not randomly, 49 subjects were treated. I just made up my own word and just threw it in there. 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. Now, I actually covered part of this section already in class, in my face-to-face class, and I didn't realize, I was like, oh, there's no useful information on this first screen. There actually is one piece of, I mean, of course, the background information is just useful in general, but as far as numbers that we need, there is one number from this screen that we need, which is the sample size. It's 49. I don't know why the 4 looks like it's bold and the 9 looks like it's not. That's kind of weird. All right. Now, this is a continuation of the same problem. And the 4 looks kind of darker here too. That's really strange. The changes in their levels of LDL cholesterol, which is the bad cholesterol, and the units of these changes is in milligrams per deciliter, have a mean of 0.4, which is not much. So again, to give you a sense, you might say, oh, that might be a lot. You know, I don't know. I don't know if I should share my personal health situation, but I think the last time I had my cholesterol levels checked, I think my LDL, I think it was in the range of like 130 something. And it told me like, it's kind of, you want it to be a little lower than what it is. So it wasn't like bad that I had to really be worried about it, but it wasn't like in the ideal range either. So I think that's somewhere in the 130 range. So if your LDL cholesterol level is like 130 and you can change it by 0.4, that's really not much. That's not much of a change at all. So, which means just right away, you can kind of tell like this garlic stuff doesn't seem to really help, right? And the standard deviation is 21. So that's a huge standard deviation relative to the mean, right? So think about that, right? That's a large degree of variation, which just means garlic doesn't seem to have any like predictable effect, right? So some people, like if you go one standard deviation below, they're actually having a mean change. Well, let's think about this too. This is a mean change that's positive, which means that the average outcome was that people's LDL cholesterol actually went up, which is bad. You want the change to be negative, right? So some people maybe had a negative change, but some people, if you go one standard deviation above, they might have had their LDL cholesterol go up by 20 points, which is really bad, right? So just crazy variation. And I hope that the numbers I'm sharing are in the same units, milligrams per deciliter. Maybe, because my cholesterol is like 130 something, but maybe the units are not this. So I don't know. Maybe I'm mistaken. But anyways, I don't think, especially compared to the standard deviation, this is much of a change in cholesterol. Construct a 95% confidence interval estimate. All right, so there's a confidence level. By the way, I circled these, but this is the mean. This is the sample mean. So that's X bar. We didn't have to calculate it. It's just given to us. And this is the sample standard deviation, 21. Alpha is going to be 1 minus that confidence level, which is 0.95. And so alpha is equal to 0.05. All right. Okay, so we want to construct a confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. What does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? All right, so that's what we want to be working on. I guess I'll go ahead and do that on this screen. So, like we did in 7.1, it's a rabbit hole. I don't know how to describe it. It is, it's a maze. Maybe that's another way you could describe it. The top level of that maze is this formula here. This is ultimately what produces the final answer. This formula for calculating the confidence interval, right? And we already know half of the information we need. It's a little misleading to say that because half of it's just given to you, and the other half you really have to do a lot of work to find. But we know the sample mean. It was just given to us. It's 0.4. We can just go ahead and plug that in. Same thing here. Sample mean, 0.4. What we don't know is the margin of error. So I don't have that information. So I'm at a dead end with this formula. I have to pause that and now go after the margin of error. There's a whole separate formula for the margin of error. It's T sub alpha divided by 2 times S over the square root of N. S, we know, is equal to 21. Right? So that's given up here in the problem. That was the standard deviation of the sample. N is 49, so we get square root of 49. But what we don't know is T. That information was not given to us. So again, we have to pause what we're doing here and go look for that missing piece of information. Right? The critical value, as it's called. Now to find the critical value, we need to know alpha, which we already identified was 0.05. We're going to have to divide that in 2. So 0.05 divided by 2, which gives me 0.025. That's the area that I want to put in the left and the right tail of the t distribution. So draw a t distribution. And we're going to put 0.025 in the left tail and 0.025 in the right tail. And we want to find, let me try drawing. See, I'm getting aggravated. See that 2, I don't know why. Some reason, I don't know if I'm just not, using the pen correctly when I'm drawing the 2. I think I'm starting the motion of drawing a 2 before the pen actually reaches the pad. And so by the time the pen reaches the pad, I'm already like halfway through my arc, and then it just gets the back end of the 2, which looks like this. It looks like an alpha, right? So sometimes my 2s look like that, and it kind of bugs me. So I'm sorry. I don't know why I'm getting so aggravated with that today. And my zeros, like this was driving me crazy earlier because like I just can't, this one worked out really well, but like this is pretty common for my zeros. They just don't connect back up at the top. And I don't, like on paper, I do it fine. On the chalkboard, on my smartboard in my classroom, I don't have that issue, but on this thing I do for some reason. So anyways, all right. Now to find the critical value, we want to find this number here that's associated with that area being in the left tail. We will do that by using inverse t. Now I did lowercase t on the last one, but I think in my calculator it's a capital T. We want the area to the left, which is 0.025, and then the degree of freedom, which is 1 less than the sample size. So my degree of freedom, let's kind of try that again though. Okay, degree of freedom is n minus 1. N was 49 in this problem. So 49 minus 1 is going to be 48. That's the degree of freedom. Oof. Let's try that again. Let's just try that part again. See, I don't know why this is bothering me so much. All right, 48. And that's what we type into our calculator. So inverse T is part of the same menu as inverse norm and normal CDF and binom CDF and binom PDF, where all those functions are located. It's under the distribution menu, which you get to by going to second vars on your TI-84. And on my calculator anyways, inverse T is just below inverse norm. So I'm going to select that function. I'll do 0.025, comma, 48. Hit enter. Like I said, it kind of drags for a second because it's evidently a fairly challenging calculation. And we get negative 2.0, is it 0? Yeah, 0.0106. I think that's as far as I'm going to go with that. All right, drop the negative, and that's going to be your critical value. T sub alpha divided by 2 is equal to that number. Okay. Out of curiosity, what would it have been if this had been a normal distribution? Right, for a normal distribution, area being 0.025, you don't have to do degree of freedom for a normal distribution. It would have been 1.96. So it's pretty close, right? 2.01, it's pretty close to 1.96. If the sample size was increased, so let's raise the degree of freedom, because I'm just curious how close it will get. Let's say if we raise the degree of freedom to 150. Let's see what that does. All right, it's kind of a slow calculation. So if the degree of freedom is 150, the T value becomes 1.98, 1.97. And so, which is a lot closer to 1.96. So as I mentioned earlier, the larger the sample size, the more the T distribution resembles the normal distribution. All right, so we don't have to worry about that anymore. I was kind of worried. I was like, is that right? I said it, and then afterwards I had a doubt, but that is how it seems to be working. All right, so now that we know T, we can go back to our calculation for the margin of error and finish that. Right, we can finish this calculation now. So let's erase that question mark because we know what it is. And so let's go ahead and put that in. So we have 2.0106. Right, should get multiplied to that. So let's go ahead and take 2.0106. Again, I might be rounding a little too much. So if you find that when you're doing the homework, if you're rounding these numbers like I am, and then you get the answer and it just keeps being wrong, and then when you check, you're like this close to it, but you're off by a couple decimal places, it could be because of rounding issues. So maybe in that case, you shouldn't round as much as I'm rounding on the video. So we have 2.0106 times 21 divided by the square root of 49, which is 7, but I'm just going to do square root of 49. And I get a margin of error of 6.0318. All right. Now that I know the margin of error, I can go back to my original calculation and fill in the missing information, right? So I don't need these question marks anymore. I know what those values are. So we'll have 0.4 minus 6.0318, and we'll have 0.4 plus 6.0318. And so we're going to end up getting 0.4 minus this number, which is going to be negative 5.6. And I don't know how many decimal places my stat lab will want you to round. I'm just going to go 2 decimal places. It might only want 1. The mean stays in the middle. That's the thing we're estimating, the population mean. And then this one's pretty easy to calculate. It's 6.4318. Well, I was only going to go 2 decimal places. Sorry about that. All right. So 2 decimal places would be that. All right. And there is our 95% confidence interval estimate. So remember, the correct interpretation of this result is that we are 95% confident that the true value of the population mean is between negative 5.63 and positive 6.43. What is not correct to say is that there is a 95% chance that it's between these two numbers. That is not true. Either the actual population mean is between these two numbers or it's not. It's not a 95% chance type of thing, because then that insinuates that the population mean is changing, and that 95% of the time it's between these two and 5% of the time it's not. That's not how it works. It's a fixed number. We're trying to estimate this fixed number, and either it's between these two numbers or it's not. Right? But if I were to construct more confidence intervals, so I only did one because I only have one sample to work off of, but if I did another study and constructed another confidence interval, and then did another study and constructed another confidence interval based on that study, 95% of the time I would have a valid estimate that actually does contain the population mean, and 5% of the time I wouldn't. My estimate would be bad 5% of the time. And there's no way to know which one's which. Is this one of the 5% bad ones, or is it one of the 95% good ones? There's no way to know. All right. So what does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? It is inconclusive, and even given that it's inconclusive, so what I want to say is the change is so little either way, it doesn't even really matter. It just does not seem to be effective. But we cannot actually even conclude that it lowers or raises, right? So a negative change means it's lowering the LDL cholesterol, and that's possible. There are, in this estimate, we do have negative values in the estimate. So it's possible the population mean is negative, and that the average result is that it does lower LDL cholesterol by a couple of points, right? But it's also within the estimate that the mean is positive, right? That's another possibility given this estimate. And if the mean is positive, that means that actually the net result is that it's raising LDL cholesterol. So maybe by consuming garlic, maybe it changes your appetite, it changes your eating habits, and you end up getting more cholesterol instead of less. It's also possible that the mean is 0, right? 0 is within this estimate. And so it's possible it has no effect at all, right? So it's inconclusive. Any of those three could be true given this range of values, right? So if we want to actually have a definitive conclusion, here's what would have had to happen. So here is a mean of 0, the mean change being 0, meaning no effect whatsoever. In order to conclude that garlic definitively lowers cholesterol, the range of our estimate would have to be completely in the negative. So if, for example, hypothetically, we did a confidence interval and the estimates went from like -10 to -3, then we could definitively conclude that garlic there's a correlation, I shouldn't say a causation, but that people on this garlic treatment do end up with less cholesterol, right? Because every value in this range is negative. So that means the mean is very likely to be negative, which means that it does lower cholesterol, right? That's what the data would suggest. So if this had been our estimate, then yes, we would say garlic lowers cholesterol. I'm just going to put LDL. I don't feel like writing out the word cholesterol. Okay. If, on the other hand, our range of estimates were both positive, it was completely in the positive side of the real number line. So let's say that we had from 3 to 10, for example. So when we did our confidence interval, we got 3 to 10 as our range of values. In that case, we could definitively conclude that garlic raises cholesterol because the mean change would seem to be positive, because every value in our estimate is positive. It makes it very, very likely that the mean is positive. The population mean is positive, which means there is a positive change, which means the LDL cholesterol is going up. So here we would conclude that garlic, if I could spell garlic, garlic raises LDL cholesterol if this had been our result. But the result that we got, that it could be between -5.63 and positive 6.43, is the inconclusive result. You can't make a judgment either way, because if the mean happens to be over here, then the average outcome is that it's lowering cholesterol. If the mean happens to be on the other side of 0, then the average is raising the cholesterol, and either of those are possible. Given our estimate, it could be negative, it could be positive. So we have to accept either possibility, we have to accept either as a possibility. And we also have to accept as a possibility that 0 could be the mean, in which case there's no change whatsoever. And so this is inconclusive. So to answer the question more directly, we would say it does not appear that garlic affects cholesterol, because for one thing, the change is small, right? It's from -5 to +6. That's not changing it very much. So it doesn't seem to be effective. That garlic, I left out a word here. That garlic is effective in changing. We're not even talking about lowering. We're just talking about, does it change the LDL cholesterol, right? But it's inconclusive, right? We really can't say one way or the other. It's unclear. Oh, geez. Okay. Can't spell. If garlic raises, lowers, or has no impact. It's not clear which one of those might be the case. Right? It's unclear if garlic raises LDL cholesterol, lowers it, or has no impact whatsoever. Sorry, my handwriting's so awful. I hope that it's legible enough, especially since I'm reading it as I'm saying it. I'm not really reading it. I'm saying it as I'm writing it. Okay. Anyways, we're 40 minutes into the video, so I need to keep things moving. We have a couple more examples to look at. But that's how you construct the 95% confidence interval. And that's the conclusion that you should draw from this. Either one of these. And of course, on MyStatLab, it'll be multiple choice. So I'm not sure what it might decide to say. I don't know which aspect it's going to address. That the change is small, so it doesn't seem to really be effective, or that it's really unclear whether it's raising, lowering, or just has no impact at all. So it should address one of those issues in the conclusion, or maybe it addresses both of them. I don't know. Okay. So I wanted to revisit the Animal Crossing critic review scores from chapter 3. So here's that data set. And we already calculated the mean and the standard deviation on that data set. So I don't think you'll have one this bad on the homework, but sometimes on the homework, for a problem, they're going to say construct a confidence interval for the mean. Here's your sample. And they'll just give you this set of numbers. And what you'll have to do is take that set of numbers, type it into your calculator, run one var stats to get the mean of that sample and the standard deviation. And they're not going to tell you what it is. You're going to have to calculate it yourself. But I say you have to calculate it yourself. You're going to have to type it into your calculator to get that information. It's not just going to be given to you. All right. Now, we did that previously. And so what I did before I started recording is I went and found that spreadsheet where we have that information, and it's located right here. So the sample mean of those critic review scores, I can barely see it. Let's just round to one decimal place, is 90.6. And the standard deviation is 6.1. We'll just go one decimal place on both of those. So that's here. That was from the spreadsheet where we did that calculation. So just be prepared that the problem you're given may not tell you those numbers. You might have to calculate it by running one var stats. Construct a 99% confidence interval estimate for the mean Animal Crossing review scores given by critics. Okay. And then we'll talk about these questions here in just a second. So let's go through the same exercise that we just did. In fact, well, I don't know, let me see what's next after this. Okay, if we know the standard deviation, so these are kind of different. So how about we do this, right? Why don't I do this off screen? So I'm going to pause my recording, construct the 99% confidence interval, and then resume the recording and show you the result. Why don't you pause the video that as you're playing it and try to work out the problem yourself, and then resume the video to see the answer, and you can check your answer against the answer that I come up with. Okay, so let's start from here. So alpha in this problem is equal to 0.01. So that's 1 minus the confidence level, which is 99%. That gives me 0.01. I divided that by 2 to get 0.005. That's the area I put in both the left and the right tail. And then from that area, I compute the t-score, the t-value for that area by doing inverse t, area to the left, and the degree of freedom. Right. So now this is going to bother me again. Let's see, that 0 didn't quite close there. So there we go. Okay. And the degree of freedom, and I forgot to mention this before I told you to pause the video. I don't know how many students are actually doing that when I ask them to do that, but if you did, I apologize. I forgot to mention, but maybe you remember there was 107 critic review scores altogether. So n is equal to 107, which means the degree of freedom is 106. So that's what I type in as the second number in this function. It does the calculation. It gave me negative 2.623, and then it was like a few zeros. So I thought it's pretty safe to round right there because the next couple of decimal places were just zeros. I drop the negative, and that becomes my critical value. So that's how I got the critical value, and that's what you should have come up with as well. All right. Now that I have the critical value, I can find the margin of error. So I go ahead and plug that in for t. S, as I already mentioned before you paused the video, or before I paused the recording, was 6.1. N is 107. So I do that calculation, I get 1.55. It's a pretty small margin of error considering the size of the numbers in the data set. And now that I have the margin of error, I can calculate the confidence interval. It's the sample mean minus the margin of error, which gives me 89.1 if I round to one decimal place. And that's the lower estimate. The upper estimate is going to be 92.2. It's the mean plus the margin of error. So 90.6 plus 1.55, round to one decimal place. And we get this. And so we can be 99% confident that the true value of the population mean is between 89.1 and 92.2, which is, for a 99% confidence level, that's a pretty narrow range. So I think I mentioned this in 7.1, that the higher your confidence level, the wider the net has to be in order to make sure you capture that population, in this case, population mean. Right. So if I want to be more confident in my estimate, the estimate has to get wider in order to make sure to capture the value that we're trying to estimate. That being said, even with a 99% confidence requirement here, this is still a fairly narrow range. That's a really small margin of error. And part of that is because the standard deviation is fairly small. There wasn't a lot of variation in the data set. But also, we had a pretty good sample size. So both of these things drive the margin of error down, right? A smaller standard deviation makes E smaller, and a bigger value for N makes E smaller because you're dividing by this, right? And so both of those really drove the margin of error down to a pretty small number. All right, if we had done a 90% confidence interval, it would have been a narrower range. The net would have not been as wide, and it would have been really close to the mean. It would have been like maybe, 89.9 to 91.1 or something. I don't know, I'm just guessing, but it would have been narrower, right? Now, the question in the problem is, based on the results, does the claim that the average critic gives this game a 90 or more seem likely to be true? I don't know if that's a really good way of phrasing that. We cannot be certain of that. So if you're talking about a score of 90 or higher, this estimate allows that the population mean might be less than 90. Not much less, but the population mean could be 89.1. It could be 89.2, right? So it could be below 90. That's within, so our 99% confidence applies to all the numbers in this range. So I'm just as confident that the mean is 89.1 as I am that it's 90.6, as I am that it's 92.2. My 99% confidence is that it's between 89.1 and 92.2. And so I'm 99% confident it's going to be between those two numbers, which means I'm confident that it could be as low as 89.1. In which case, it would not, the claim that the average critic score is greater than 90 would be false, right? So it's possible that it could be false. It's possible that it could also be true, right? Because it's also possible the mean might be 91. It might be as high as 92.2. That's also possible given our estimate. But we can't definitively say that for sure the population means greater than 90 because our estimate allows that it could be actually a little bit less than that. And we have to take that seriously as well, right? And so again, going back to the drawing we had on the last problem, doing something similar here. Here's 90. That's the score I was concerned with. My estimate goes from 89.1 to 92.2, right? And so I'm confident, I'm 99% confident it's somewhere in here. But it does allow for the possibility, a very strong possibility, that the mean critic review score is less than 90. So if I made a claim, and I said my claim was the mean critic review score is 90 or greater, this actually does not support that claim, right? Because it allows for the possibility that it could be less than 90, right? Now, the other claim that the mean critic review score is greater than 80 is supported by this confidence interval, right? So if I compare this range relative to 80, definitely, right, every value in this ranged estimate is above 80. And I'm 99% confident it's somewhere over here, so I'm 99% confident it's above 80, right? And so it does support that claim. So this does not support the claim. See if I can write a little bit nicer this time. Does not support the claim that the average score, which I'm just going to say mu, is greater than or equal to 90. It doesn't support that because there are numbers less than 90 that could also be the mean, according to our estimate. Right. But it does support the claim, that the mean is greater than or equal to 80. That is definitely supported by this. All right. Now we're going to be talking more about claims and supporting or rejecting or not supporting, not rejecting claims in chapter 8. So this is a little bit of a primer for that, like trying to understand what the confidence interval is telling us about our set of data, what we can know is true versus what's not true, answering questions like this using the confidence interval. We're going to formalize that in chapter 8. Okay. Now, the next segment of this video is going to be constructing a confidence interval, knowing the population standard deviation. So if for some weird reason, we know the population standard deviation, which is sigma, right? So sigma, this is what we're talking about here, is known, but we don't know the population mean, hence we are trying to estimate it with a confidence interval. If that's the case, if you know the population standard deviation, this becomes the formula for the margin of error. And you will use sigma, since you know what that is, and we go back to using the normal distribution. So z, whenever you see z, that's always in reference to the normal distribution, and to find that we're going to use inverse norm, not inverse t, if we know the population standard deviation. So let's take a look at some problems to decide, like based on the scenario, when would we use the t distribution, when would we use the z distribution, and when would we use neither, right? So that's also a possibility here. And then we'll do an example of finding the confidence interval when we know the population standard deviation. So here n is equal to 25. That's the sample size. Population standard deviation is known, so we know what that is. Population appears to have a normal distribution. All of these make it so that we can just use the z or the normal distribution, right? If you know the population standard deviation, you can use the normal distribution to estimate the population mean, right? N is equal to 40. The population standard deviation is unknown, so I cannot use z. If you don't know the population standard deviation, z is ruled out. I can rule out z. So how do I want to write that? Z cannot happen. Cross it out. Population appears to be skewed. That's okay as long as the sample size is bigger than 30. So because the sample size is greater than or equal to 30, we can still use the t distribution. So for B, we would use the t distribution to estimate to construct the confidence interval for the population mean. And I'm sorry, it's kind of hard to see that that's a t. Let me undo that. Okay. My t's, it's just not going to look good there. Okay, so from this, we know that for part B, we can use, for part B, we can use the t distribution. All right, for part A, we can use the normal distribution because we know the standard deviation, the population standard deviation. N is equal to 9. Population standard deviation is unknown, so again, if you don't know the population standard deviation, z is out. So it's either t or bust, right? We just can't do anything. Population appears to be very skewed. That's okay as long as the sample size is bigger than 30, but it's not, right? So because n is less than 30, t is out also. And so we can't do either. So the answer in this case for part C is neither. We can't use either one. Right. Sample size is 18. Standard deviation is unknown. Well, we don't know the standard deviation, so Z is out. Population appears to be normally distributed. That's fine. If the population has a normal distribution, then the sample size doesn't matter. We can still use T. Right? So because this has a normal distribution, T is good. The sample size doesn't have to be less than 30. So I guess I have to be careful about crossing this out. It's because of this and this, right? Those together kill the T distribution. But if you have normal distribution for the original population, or if the sample size is bigger than 30, then you're okay to use the T distribution. Okay. So people have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably, so we need to update our estimate of that mean so that boats, aircraft, elevators, and other such devices do not become dangerously overloaded. So what we're talking about here is the capacity, right? So if you go in an elevator, they usually have a sign that says maximum capacity for this elevator, and they give a number. The number they're giving is based on what they assume is the average weight of people. Now, here, I don't know why we're focusing on men in particular, but, if the elevator says the maximum capacity is 18, that number is arrived at based on assuming the average weight of a person is X pounds, and that if, you take a group and everybody weighed the average, you could have 18 people on there safely. But if you have the wrong average, then that capacity might not be accurate. And so if people are actually heavier than the average you assumed, then you should have less people on the elevator. And by allowing 18 when really, based on the actual average, you should only have 16, it could be dangerous if 18 people got on the elevator, right? So in a sample data set, we obtain these sample statistics for these simple random samples. So we're being given the sample here. Or I guess we're not being given the sample. Sorry, it seemed like that was kind of the setup there. In a sample data set, we obtain, I repeated it here. So we're just being given the information we need. The sample size is 40, and the sample mean from that sample is 172.55 pounds. Research from several other sources suggest that the population of weights of men, has a standard deviation, a population standard deviation, by the way, given by 26 pounds. So again, it's still just a guess, but we're going to assume it's such a reliable source that we can almost be certain that that's the population standard deviation. It's 26 pounds. So we're going to use that as the population standard deviation. So find the best point estimate of the mean weight of the population of all men. The best point estimate, remember, point estimate means if you had to pick just one number to estimate the mean, what would you pick? And the best one number estimate for the mean is the sample mean, which we don't have to go find. It was given to us, right? It's this. That's the best point estimate. I'm just going to repeat that for part A. I don't have to actually calculate it. I'm just going to copy it from the problem I was given and paste it as my answer, basically, right? 172.55. That'd be the best point estimate. 172.55. All right, part B, construct a 90% confidence interval estimate of the mean weight of all men. All right, so we'll go through that process. But this time, since we know the population standard deviation, we know it, we will use the normal distribution and we'll use z-scores as our critical value rather than t-scores. So we don't need degree of freedom, we don't need to use inverse t, we're going to use inverse norm instead when it gets to that point. We're going to use the slightly modified version of the margin of error formula for knowing the population standard deviation. So let's just stop talking about it and let's just get it done. All right, so the formula for the confidence interval is exactly the same. It's the mean minus the margin of error for the lower estimate, mean plus the margin of error for the upper estimate. I already know the mean. It was given to me. It's 172.55. But I don't know the margin of error, so I'm going to leave a little space for that. Again, the mean I know is 172.55. Plus, I don't know the margin of error. Leave a space for that. So I need to find the margin of error. So that's my next step. But this time the formula is z sub alpha divided by 2 times sigma over the square root of n. It's really the same formula. We're just switching to the normal distribution and switching the symbol from s to sigma. But it's still critical value times standard deviation over square root of n. Both formulas have that same exact structure, right? But this one, it's sigma standard deviation. It's the population standard deviation. And because of that, the critical value is z instead of t. All right. Now, we have the estimate for the population standard deviation as 26 pounds. The sample size, I think it's 40. I already forgot. What was the sample size? All right, it's 40. Okay. So sample size is 40, but I don't know this critical value. So I have to pause this calculation and go find the critical value using alpha, right? Now we wanted a 90% confidence interval. So that's going to be 1 minus 0.90, which gives me a value of alpha of, said that weird, sorry about that. It gives me a value of 0.10 for alpha. Right? But I have to divide that in 2 because that alpha has to cover both tails, the left tail and the right tail. And so that's the area that needs to go in the left tail and the right tail. So let me slide over a little bit more here. So we're going to draw our normal distribution, which looks just like, and I'm starting to slur my words now. I promise I'm not drinking. I'm just tired. So what was I even saying? We're drawing our normal distribution, which looks like the t distribution because they look the same. They're both normal. They're both bell-shaped curves. That's what I'm going to say. I'm about to lose it. Okay. So we put 0.5 in the left tail, 0.5 in the right tail, 0.05 in the right tail. To find the critical value associated with that area, I guess I wanted to put a question mark there. It's usually what I do. That's going to be inverse norm, right? Because we're using the normal distribution. We're finding a z value, which is the normal distribution. So I use inverse norm. Area to the left is 0.05, and that's all I need. Right? I made that mistake earlier, right? For inverse t, I was like, okay, area to the left. But for inverse t, you have to have the degree of freedom, but not for inverse norm, right? So we just do inverse norm, 0.05, and we get negative 1.645. You know, the mean is given to 2 decimal places, so I really feel like the margin of error and the critical value for that matter, I should go a couple more than that just to be safe. So I did 5, but that's if you rounded it to 3 decimal places. It's 64485. Let's just go that far. That should be fine. Drop the negative sign. That's my critical value. Right? Z sub alpha divided by 2. We're going to plug that into our formula for the margin of error. So we're going to have 1.64485 times that fraction. And so what are we going to get for our margin of error? Let's find out. In fact, I'm rounding it on the screen, but since it's still in my calculator, I just use the whole number in my calculator. So I don't type in 1.64485 again. It's still in my calculator. And it's negative, but I just ignore the negative sign when I get my answer, right? And I'm sorry, that looks like a plus sign. I'm sorry about that. At least from my vantage point, it does. So I'm going to take that number, multiply by 26, divide by the square root of 40. And it gives me negative, but I just dropped the negative, right? It's going to be 6.76. Now, again, my mean goes 2 decimal places, so my margin of error, I probably should carry it at least to 3. And so this is going to round up to a 2. So I kept a few extra decimal places here, but then the margin of error, I think we're safe if we just go to 3, because my final answer, I'm just going to round it down to 2. But in order to make that rounding decision, I need to know what that 3rd decimal place is. So that's why I want that to be to the 3rd decimal place. Now, for this 3rd decimal place to be accurate enough, I would need a couple more decimal places for my critical value. That's why I went a little bit further with that, so that this would get rounded appropriately when I round to 3 decimal places. So if I rounded this one off a little too much, it might not be right to the 3rd decimal place. It might be, off the mark by the time I got to the 3rd decimal place. So that's my reasoning. Hopefully I'm keeping enough decimal places that our answer is accurate enough to make my stat lab happy. And again, I don't know why I'm slurring my words. Okay, so plug in this number for E. I know why. It's because I'm tired. I need to have a break. Okay. So, and then there's my confidence interval. So we have 1, again, it's still in my calculator, and it's still negative. So if I just add 172.44, sorry, 44, 172.55, just making up numbers. Oh, wow. Okay. I get 165 point, I'm going to go 2 decimal places, 79. Okay. And then for the upper estimate, 172.55 plus 6.762. Round that to 2 decimal places, I get 179.31. Okay. And that is my 90% confidence interval estimate for the mean weight of men. Okay, that the average man weighs between 165 pounds and 179 pounds. I'm 90% confident in that estimate given the data that we have. That's part B. Part C, what do the results suggest about the mean weight of 166.3 that was used to determine the safe passenger capacity of water vessels in 1960? Well, according to our estimate, that is still possibly the mean, right? It may not have changed. It might still be 166.3 because that actually fits within our ranged estimate. But it's really on the low end. And so I would think probably the actual average is higher than that. There's a good chance that it's higher than that. But this would not prove this wrong, right? This is still a possible mean for the average weight of men. So maybe it's still a good estimate for determining passenger capacity. Right? We couldn't rule that out. Now, if my estimate went from like 167 to 179, then 166 is left out of that estimate, and I would be able to then definitively conclude that this is wrong, right? This mean is not correct. I'm 90% confident that that mean is not the actual population mean. But I can't make that statement given this ranged estimate because this value is actually included in that estimate. And again, that 90% confidence applies to all the numbers in this range. So I'm just as confident that the mean is 166.3 as I am that it's 165.79, as I am that it's 179.31, as I am that it's 172, right? Could be any of these numbers. I'm 90% confident in all of them. And so I can't rule this out as the actual mean. So maybe they don't need to revise their capacity at this point. Okay. That's what I would conclude. Now, again, on MyStatLab, you'll get these statements, A, B, C, and D. It's really kind of different. You've probably already experienced it in some other of the homework that you've already done. But they like to basically copy and paste the sentence so they all look almost the same. And they change one word here, one word there. So you have to read them very carefully. But you want to find the one that says something to the effect of that this mean is still a possible value for the population mean. That 166.3 could possibly equal the population mean. And so that, how do I want to say this? So suggest about the mean weight. So the passenger capacity might still be valid. Right? There's we're 90% confident that that passenger capacity is still valid. Okay. Now, we talked about this in section 7.1, determining sample size. So if you have some particular margin of error that you would like to target, because if you just pick some random sample size and do your calculations, you might get a crazy big margin of error, which makes your estimate not as helpful. So you might want to guarantee a certain margin of error to give you a more useful estimate. But in order to do that, you'll have to figure out what sample size you would need to have in order for the margin of error to be as low as you want it to be. And that's possible. You can do that. This formula allows you to do that. Well, not this one, actually. There's an issue with this one. Whoops, sorry about that. I meant to circle it. There's an issue with this one. The problem is, I could solve this for n, and I could get n equals whatever, from this formula. In fact, what you would get, let's just talk about what it would be. It would actually be, what is it going to be? T squared times s squared over e squared. I'm pretty sure that's right. Right, so yeah, divide, yeah, that's right. Okay, so alpha divided by 2, this is what it would be. So if you took this formula, solved it for n, this is what it would be. And then all you have to do is plug in these numbers on the right-hand side, and that would tell you the sample size. But you'll run into a problem. That problem is, how are we going to calculate t? Remember, to calculate that, you're going to use inverse t. You would need the alpha divided by 2 as your area, but you would need the degree of freedom in this function in order to calculate that value of t. That degree of freedom requires the sample size. So essentially, to calculate the sample size that you would need, you would have to know the sample size in order to find the degree of freedom to get that value of t. So it's circular. You can't, it's impossible. I can't find what n is equal to. How do I want to say this? In order to find what n is equal to, you would need to know the value of n to get that degree of freedom. So you can't, right? If you don't know n, you don't know the degree of freedom, you can't calculate t. So this formula actually cannot be used to calculate a sample size. So we have to use this formula instead, right? Z doesn't need a degree of freedom, so we don't need the sample size to calculate Z. So we're just going to have to use this formula, use our best estimate for the standard deviation as our population. We're going to call it the population standard deviation, but we really don't, we might not know it. We might have to estimate what it is, but we're going to consider it as the population standard deviation in this formula. And then we can calculate Z using alpha without needing the degree of freedom. And then we can plug in E as our target margin of error that we want. And so this would be the formula. It looks a little different than the one I had on the last screen, because on the last one, everything is squared, but you can just take that power of 2 outside parentheses, which is what I'm doing here. So you take Z times sigma divided by E and then square that whole thing. And that gives you an estimate for the sample size that you would want to get that particular margin of error. So let's give this problem a try. Now, I'm sorry, I accidentally left this slide in my presentation, so now you kind of know my secret. When I'm creating a new presentation, I just copy the last one, and then I just edit things out. And so, because, I knew I was going to talk about sample size again, right? That's what I did here. So that way I still have the same heading. I just switch out the formulas. And usually I would delete the original slide, but I forgot to do that here. So sorry about that. Okay, this is the last example. We're almost done. Assume that we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ test if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? Assume the population standard deviation is 15, right, which is what it's supposed to be for the population in general. But we are narrowing our consideration to just statistics students. So the mean IQ score of the general population is 100, but maybe for statistics students, it might be different. It might be higher, it might be lower. We don't know, right? But we are going to assume that the standard deviation doesn't change. So we're going to use the population standard deviation of 15 as the standard deviation of IQ scores for just statistics students. Sorry, that's a funny looking sigma, but we're near the end. I'm just not going to worry about it. We're just going to leave it the way it is. So the formula we want to use to estimate this is n equals Z sub alpha divided by 2 times sigma over E squared, right? So we have sigma here. We're going to plug that in. So 15 gets plugged in here. We want to be within 3 IQ points. We want our estimate to be within 3. That's the margin of error. So we want the margin of error to be 3. So we know E. So the last thing I have to do is calculate Z, right, which is based on alpha. We want a 95% confidence interval. And so it's going to be 1 minus 0.95, which is going to be 0.05. We have to divide that in 2 to put half in the left tail, half in the right tail. And so that's going to give me 0.025. And again, for Z, if you already know this one, you might have this memorized. Because for Z, every time it's a 95% confidence interval, the value of Z is the same. It's always 1.96. I think that's what it is. I feel like I want to go ahead and calculate it because I'm like, maybe I've forgotten it. But I don't trust my memory too much right now. So let's go ahead and calculate that. We're going to put, but if you know it or if you have it written down, it's going to be the same. If it's a 90% confidence interval, that's always the same. So this is going to be 0.025 if it's a Z-score. I don't know if I mentioned this earlier in the video, but for the t-distribution, you can't memorize. So even if you're doing two t-distributions that both are 95% confidence level, the t-values will be different for each problem because the t-value is also affected by the sample size. So unless the sample size is also the same, the t-values will be different. But for the normal distribution, 95% confidence interval, it's the same every time regardless of what the sample size is. The z-value will always be the same every time. All right. So that might save you from calculations every once in a while. All right, so to find this value, we're going to do inverse norm. Area to the left is 0.025. And that's going to give me inverse norm 0.025. Yes, it's the number I thought it was. So we're going to get negative 1.96. We drop the negative sign. That's going to be our critical value. So plug all these numbers in. You get 1.96 times 15 divided by 3. Raise that to the second power. Right? So 1.96 times 15 divided by 3. Square that answer, and I get a sample size of 96.04. Now it's a 0.04, which means this number is really close to just the number 96, but we always round up, right? So when we're estimating sample size, we always want to round it up to the next whole number. So we're going to round that up to 97. And so that would be the sample size that you would want to try to guarantee, again, whether it actually works out kind of depends on what the standard deviation ends up being, but 97 is the sample size that you would want to try to have a margin of error of 3 for this scenario. All right, so that concludes the video on section 7.2. I will see you in the next video. Thank you for watching.